In this video I'm going to go through a second kind of changing state example. This one's a lot trickier. It's a higher level example. It's on page 107 of your textbook, and it's very similar to the experiments that you do for this topic. So if you can get this, really you can understand the experiments. So what have we got? We've got 50 grams of iron, which is at 120 degrees Celsius. So let's just do a little diagram here. Here's a little block of iron, and the iron is at 120 degrees Celsius, and its mass is 50 grams. Now remember, 50 grams, you always need to change that to kilograms, so divide it by 1000. It's 0.050 kg. That's right, isn't it? 1, 2, 3 decimal places. So this iron is added into water, and we have 120 grams of water, and the water is at 25 degrees Celsius. Now obviously water is going to have to be contained in something. So this is our cup. Now the container that we use in this experiment, it's just a little cup, and it's usually made out of copper, and it's called a calorimeter. And it's metal, and because it's metal, it's copper obviously in this case, it's a really good conductor. So if you have a hot drink in a metal cup, you can feel the heat. You can't pick up the cup because it's too hot. Or likewise, if you have a cold drink in the cup, you can feel the cold. So what we take from that is that whatever the temperature of the water is, the cup will be the same temperature. Now obviously that won't happen straight away because the water will heat up, and what happens is heat moves from the water out to the cup. But we just assume that once the temperature of the water has reached a certain amount, the cup will be the same temperature. And for that reason, we need to include it into our calculations. So we have 120 grams of water, which is 0.12 kilograms of water. And the water is at a temperature of 25 degrees Celsius. So what we assume then, this is the water, we assume the cup is at the same temperature. So assuming, oh sorry, I read the question wrong. It's 100 grams, it's 120 grams of water, but the copper calorimeter itself, the calorimeter, has a mass of 100 grams, so that's 0.1 kg, and its temperature, as I said, will be the same as the water, 25 degrees Celsius. So these are the kind of three factors. We have the iron over here, we have the water, and we have the calorimeter. Now when you do this experiment, the calorimeter is actually surrounded by insulation. And the reason it's surrounded by insulation is that obviously when we're trying to figure out how much the water heats up, we don't want to kind of have heat loss to the surroundings. So that will make a little bit more sense when I go through the question. So assuming the calorimeter is the same temperature as the water, and there are no external heat losses, we have our insulation, calculate the final temperature of the water. So if you just kind of overall picture what's happening here, we have a hot piece of iron, 120 degrees Celsius, and we're putting it into colder water, 25 degrees Celsius. So obviously we're going to assume the temperature of the iron will decrease, and the temperature of the water and calorimeter, remember they're both the same, will both increase. And that makes sense. If you put something hot into something cold, there's going to be heat transfer. So the key to this question is remembering the law of conservation of energy. And that basically is that energy lost is equal to energy gained in this case. So what's going to happen is the hot piece of iron is going to lose some energy, and the water and the calorimeter are going to gain energy. So how do we figure out how much energy the piece of iron loses? Well, it's going to lose mc delta theta worth of energy, where delta theta is the change in its temperature, m is its mass, and c is its specific heat capacity. So that's for the iron. Now the water and the calorimeter are both going to heat up, so they're gaining energy. So how much energy do they gain? Well, mc delta theta for the water plus mc delta theta for the calorimeter, CAL. Now the tricky bit here is we know lots in this. We know the mass of every item, we know the mass of each one. In the question, they've given us all the specific heat capacities, so we know C. So we know all that. What we're looking for is the final temperature of the water. And in our equation, we don't have final temperature, we have change in temperature. So what we're going to have to do here is we're going to have to use a variable to kind of solve that. So the initial temperature of the iron is 120. It's going to cool down to some temperature. Let's call that temperature T. So the change in temperature of the iron will be 120 minus T. That's how much its temperature changes by. Now the water started at 25 degrees and that's going to increase its temperature to T. So the change in temperature for the water will be T minus 25. Because T is going to be bigger than 25, let's say it's 40, the change in temperature would be 15, 40 minus 25. But we don't know what T is yet, so we just call it T. And the calorimeter likewise, it's at 25 degrees Celsius, it's going to increase to T, so the change in temperature will be 25 minus T, or sorry, T minus 25. So now we fill in all the values we know. So energy lost by the iron would be the mass of the iron, which was 0.05 times specific heat capacity of iron, which they've given us here, which is 488, times its change in temperature, which is 120 minus T, equals mass of water was the mass of water was 120, yeah. So 0.12 times specific heat capacity of water, 4,200 given to us in the question, times T minus 25. And then finally the mass of the calorimeter was 0.1 times its specific heat capacity. Now it's copper, so that's 390 given in the question, times T minus 25. Now we've a long complicated equation here, but once you get that equation, you have the question really solved. It's just a matter of rearranging this to solve for T, because there's only one variable that we don't know in this, and that's T. So I'm not going to multiply it all out, but what you should end up with at the end is, when you can try this, 565.4 T equals 16263. And then T will be 16263 divided by 565.4, which is 28.76 degrees Celsius. So that's the final temperature of the water. So as I said, the hardest thing in this is kind of setting up the question. So draw a diagram like I've drawn the diagram. Think about what loses energy. What loses energy is what cools down. So in this case, it's the iron. Think about all the things that are gaining energy, getting hotter. So in this case, it's the water and the calorimeter. And then do MC delta theta for each one and fill in the gaps.